start with presentations. We're going to talk about scaling laws after we finish up with diffusion models from last time. Not that much left for logistics. So homework 3 will release it on Thursday. We've finished revamping it. Homework 1 grades hopefully should be finally out. You guys let me know if that's not the case. Homework 2 we're grading right now, so we'll have that soon as well. Yeah, so in 1 week we'll start presentations. I'm going to ask everybody to come who isn't coming, because we should all get to see each other's presentations. And before then, we'll have today's lecture and then kind of one grab bag of topics on Thursday, and that's approximately it. Any questions about logistics? And thank you to everybody who has been mailing me to talk about the project. Everybody should chat with me about that. You'll also send in your proposals, of course. Cool, so we'll be getting into all this stuff in just a minute. But basically what we'll talk about today is how do we know what type of design choices we should make for one of these large-scale models that we've talked about building the whole class. And you can imagine that you can't just sort of experiment with every combination the way that we traditionally did in ML, because you typically only have enough compute for like 1 or 2 large-scale training runs. So if you mess it up, basically, you don't really get that many chances to try again. You cannot do hyperparameter tuning, right? Like that's just not an option in this case. And the messing it up thing happens, like Llama 4 is famous because basically the training runs failed and the resulting model wasn't that good. And there's nothing you can do about that, right? Like you've invested all the GPUs you have into it. Once it's over, it's over. Today we'll talk about the techniques that we do to make sure that we don't end up in that situation. So these things are going to be called scaling laws. What they basically say is, I'll try to extrapolate at a larger scale what happens from results at a smaller scale. So if I can train a model with 500 million parameters, and then 1 billion, then 2 billion, and so forth, then I can draw some curve that tells me what to expect when I train a model with 100 billion or 1 trillion parameters. So we'll see how we do that. It's actually going to turn out to be fairly simple. Then we'll see that the first set of these scaling laws didn't quite work perfectly, and we'll talk about some alternatives that are a bit better. And then finally, we'll have a very brief kind of how do we go beyond these things for when we want to improve even further. All right, so let's go ahead and first start off with where we left off last time. We were talking about generative models, and we had covered a whole bunch of different cases of generative models. We had finished with this really interesting one that we call the diffusion model. And if everybody remembers this, the one thing that was special here is rather than going directly via some mapping to a latent space, which was maybe lower dimensional or some other kind of space, and then returning from there to generate new data, we said, no, we're actually just going to keep the space the same. And the way we'll get to sort of this thing that looks like a latent Z from our original point is by just adding noise repeatedly. So we're going to start with one of our samples from our true data distribution, that x0. We add noise, we add noise, we add noise, we add noise. We do this very gradually until eventually everything is noise. And that noise is our new latent space. And if we want to sample from our trained generative model, we do exactly the same thing in reverse. We start with noise, easy to sample from Gaussian noise, for example. And then we take these denoising steps. And each one removes some noise until eventually we get an image from our original data distribution or some other object from our original distribution. OK, does this track for everybody? This is kind of where we left off last time. Everybody agree with the principle? We always want to have this latent space, which looks like noise. It's cheap to sample in the latent space. And then we always need to transform back into the original data space. And the process of that transformation, in our case, is going to be this denoising process. And it's not one single function. It's a bunch of these steps that each remove some amount of noise until eventually you're left with something that looks like it's from the original data distribution. So that's the basic principle. OK, everybody OK with this? Cool. And when we talked last time, we said that this isn't really one technique. It's really more of a broad family with a bunch of different techniques. And these kind of originated in different places, but all have some things in common. All of them have something to do with noise being added in some way and then being removed in some different way. OK, and then we talked about sort of the first of these methods. And these are called score-based because they use this other sort of objective that's called the score. And the game that we were playing here is, if you remember last time, we said the hardest thing about modeling a distribution was dealing with the fact that we're talking about probabilities. They always have to sum up to 1, right? Or if they're continuous, they have to integrate to 1. And we said that means there's always some normalization constant that has to be placed in there to force these things to add up to 1. That normalization constant had this fancy name, the partition function. And we said, okay, look, if we have to compute this partition function every time, it's too expensive. This is something intractable. So all of our methods, we're trying to get around this problem in some way. And we said that one of the ways we can do that is by not directly modeling the density, but finding some way to get around it. And in our case here, for these diffusion models that are called score-based, they are going to use this object called the score, which looks like this. Again, it looks almost exactly like what we were doing before, except in this case, the gradient is not being taken, right, with respect to some parameters, in which case we would need the partition function. It's taken with respect to the data point, x. All right, everybody okay with this? So the expression looks very familiar. It's just that it's not taken with respect to the same thing. We're now talking about the data space itself. So this is the gradient of the log likelihood, but again, it's with respect to the data. And the way to think about this basically is, depending on where you are in your data space, stuff can change a lot, stuff can change a little. That's really what you're trying to track with this score function over here. Okay, now this thing trivially gets around our problem of computing the partition function. And let's see, right? The reason for that is this really simple expression. Okay, we know that our score function over here is s of x. Okay, this thing is the gradient with respect to x of log p theta of x. We've parametrized these things with some theta. And when we take that gradient and we plug in something into p theta of x here, like one of our energy functions, right? That could be a 1 over z times log times x of f, for example. Then we're going to have a term that involves the partition function, but notice that it does not depend on x, right? The partition function is a normalizing constant. It already integrated over x. So there's no further dependence on x in it. When you take the gradient with respect to x, you get 0. So therefore, I don't have to worry about this z theta, this partition function term anymore. It just doesn't play any role in here. All right, so just a little bit of algebra to see that. Everybody okay with this? Cool. So this is the trick, right? We're using an objective that doesn't really depend on the partition function. It doesn't really care, right, about having to compute this normalizing constant. And therefore, we can do something that ignores it altogether, and we can go train. Okay, now we won't get too far into the details for this. We need 2 pieces always for these generative models. One is we'll need to train, right? So we'll have to get our samples, and we'll need to find some way of training the model based on whatever principles we picked. Here it's a score. The second piece that we need is we have to find some way of sampling, which means we take our noise, and then we must restore it to the original data distribution. So these are going to be the 2 pieces here. This is kind of where we left off last time. For training, we are actually going to use this score function in itself, right? So we're going to say, hey, we should make our score that we parametrized, s theta of x, to be as close as possible to the true score that pertains to the true data distribution. Now, we don't really know the thing on the left either. We have to get it from samples, and we add some noise to the original data distribution to be able to get some estimate of the actual true score itself. So this is how this idea works. We don't really know the left-hand side here, but we can get some signal from it, from noising. And we just go ahead and run the mean squared error and just try to parameterize the score directly. Okay, now if we have this thing trained, we need to find some way next of actually sampling images. Again, this is something that's not strictly p theta, but it's not too far either. Basically, what we can do is run a process that starts with noise and then gradually, essentially, goes back to the original data distribution. And it's this guy over here. Now, this thing looks a little bit like gradient descent. It's a different type of iterative optimization process. It has this fancy name, Langevin dynamics. We can ignore the details, but roughly speaking, it's sort of taking steps in the direction of the part of the data distribution that has the most stuff happening in there. And what you're seeing over there in the ZI is adding noise to kind of make sure that we get to the right place. Now, let me show you how this looks visually, because this equation isn't super revealing by itself. Here's what we end up getting. What I'm doing here basically is I start off by sampling uniformly, or from a Gaussian or whatever you like, from this entire space. And these initial samples are these blue dots that you're seeing when we start this process off. Now, these blue dots are random, right? They're exactly the situation of sampling noise. And what I want to do is to actually transform these back into elements from my original data space. Now, you can see what's going on in this original data space. What we have here is just a mixture of two Gaussians. And these are two-dimensional Gaussians, so it's a very simple distribution. But you guys see what I mean, right? So we have one Gaussian centered over here, left lower corner. And we have one Gaussian centered on top over there, right upper corner. So that's the original data distribution. And what we'd like is to get these blue points in such a way that they're as if they're samples from this true data distribution. But what we start off with them is just placing them randomly throughout over here. So the process of transforming them is actually just iteratively following these arrows, right? And these arrows are precisely these gradients of the score function. Sorry, they're given by the score function. They're the gradients with respect to x of the density. All right, everybody see what I mean by this? All of these arrows say you should go in the direction in the data space of where there is more stuff. Go there. And then we just follow them iteratively until the process converges. And then we end up getting something that looks very believable, right? Almost all of the probability mass is either around here, close to the mean of this distribution, or close to the mean of the other Gaussian. All right, does this sound OK for everybody? Yeah?
In the previous slide, what was S theta of x?
That's the thing that we learned, this score function. And that's just this machinery that's shown here visually by the arrows. It's basically a bunch of directions for where in the data space you are meant to go to. And you just follow these directions sequentially until you converge. And then you have a bunch of points that look like they're from the original data space and the original data distribution here. Yeah?
How does this, so in theory of reasons, why does this end up producing unique samples? It seems like almost, or why does this end up producing new samples from a distribution? Because it almost feels like it should just inevitably gravitate towards pockets of samples, essentially.
It actually does, right? So that's actually an issue that we'll see in just a second. But these pockets are really what are the modes of the original distribution. So you do expect to see that most of your fresh samples are going to end up near one of these modes. But you're right, you're asking the question of mode collapse, right? What if I accidentally end up getting everybody exactly dead on the mean for this distribution by accident? Then I've trained too much, or I've done something else bad, right? But yes, that's an issue.
And when do we know when to stop?
So that's given by our algorithm that we're following. It has a convergence definition. And once we've converged, we stop, right? Now, keep in mind that this is just a visual example with tons of points. Normally, we're sampling 1 point at a time, right? So it really just moves until it's not moving any further, and then you stop there. All right, so long story short for what we've done so far, we basically said, hey, we need to model some object that permits us to sample new points. The object in this case was this score function. The score function, you can think of it visually as these arrows that tell you where to go in data space. And then our new sampling mechanism is this iterative procedure that uses the learned score and just follows it step by step until it sends you somewhere in the original data space. So it's a very similar principle to what we did before, except instead of having a one-step transformation that says, OK, take my noise that I've sampled, transform it to the original data space, we have this sequential one that says take these arrows until you converge and stop somewhere. All right, anybody confused by this? Cool. And keep in mind, again, this is just a visual. The equation we're following is exactly the one at the bottom over there. We start with some x0 sampled from our distribution, which is noise. And then we follow this procedure. This thing in the middle we have access to, right? This is the thing we learned, that score function that we were talking about. And again, we never needed to use the partition function here. And then we have this noising mechanism that helps us not immediately get lost. And we follow this procedure iteratively. We generate our noise x0, then we compute an x1, an x2, an x3, and so forth. Eventually, we converge, and we get a fresh sample. And what you guys are seeing in the image is doing that for many of these blue points. And the movements are just that iterative procedure that's kind of following all of these directions that you're seeing. Okay, so this is it. I mean, obviously in reality, we're not going to do distributions that are this simple. They're not going to be a mixture of two Gaussians in two-dimensional space. They'll be much more complex than that. But the principle is going to be basically exactly the same. So this is a pretty nice visualization. Cool. Everybody okay with this? All right, so let's keep talking about a few more aspects of the story. Here's sort of another visual depictions of things, right? We started with some data samples. In this case, we're going to pretend that our two Gaussians are really something from a richer distribution, like faces, let's say. Generative models that can output fresh samples of faces are kind of a standard thing that people do. Right? We're going to take those samples. We'll do the score matching procedure, so we have access to our trained score function. And then we can go ahead and sample new samples. We use that algorithm that looks a little bit like gradient descent to go ahead and sample some new samples. We kind of start in that picture where the arrows are. Again, we follow the arrows, and then we'll get a new face as a result. So this is sort of the more realistic version, if you'd like. Now, there are some downsides of this as well, right? One problem is, well, in areas where we have low probability, we don't have that many samples that we've seen, we tend not to be too accurate, right? This is a standard problem for any generative model. By definition, we have fewer samples from regions that have less probability mass in the true data distribution. So this is something that can be a concern. And one way that we can really sort of deal with it potentially, essentially, is by adding some more noise and making sure that our model sees more of those points. So here's the rough story, right? Our original data density, let's say, looks like this. Still those two Gaussians. Nothing has changed here. OK, now what's the problem? Well, when we get samples, they'll almost always be from those two areas. So when we go estimate our score function using the true samples, we're going to be very good at estimating these regions where all the samples come from. But we will not be so good about that red region that you're seeing there. And the reason, again, why not, is because, well, we don't have that many samples from there, right? Everything here is a function of having access to data from those regions. The less data that we have, the more inaccurate we will be at estimating anything, whether the true density, whether the score function, whatever it may be. Everybody okay with this idea? Again, this is trivially true for any generative modeling technique that we have. Now, of course, what's going to kind of cost us there, not surprisingly, is if we're super inaccurate, these arrows may point in all sorts of weird ways. And that may make it much more complicated for us to follow the arrows. In other words, to iteratively use the score function to get to where we want to go. Everybody agree with that? So here, everything says I must kind of move myself from some random noisy point that I've started with when I'm sampling. And I have to follow these arrows. And they'll eventually take me somewhere where I converge. And that will probably be a place with a lot of this probability mass. But the arrows in the meantime that I'm following might themselves not be that accurate, right? They may not point the correct way. Again, because we trained these arrows on data, and we didn't see that much data in those regions. Everybody see what I mean? OK, so that's kind of the issue here. This becomes a pretty big problem. And you can sort of see in this inaccurate version over here, if you're following the arrows, you can get stuck in various places. It can become very difficult to find high probability regions by just iteratively following them. All right, everybody OK with the idea? So this is sort of one issue that people have started thinking about a lot. And one way to deal with it, essentially, is just go ahead and perturb your original data density, which is to say your actual samples that you get, with noise. Right? And you can do this with noise at kind of different scales potentially as well. I can add noise with one standard deviation, maybe that's small. That doesn't really affect my data distribution very much. Fine, that leads to one kind of score. I can do the same thing, but with more noise, right? My sigma 2, my next standard deviation, is larger now. And this permits me basically to actually have somewhat better estimation of scores in these other regions. And same thing, I can do the same thing again with something even larger potentially. So having these noise at different schedules actually permits me to see more of my data space, and therefore to learn better estimates of the score function. And that means when we actually go sample, we don't get stuck nearly as much. So a lot of the work for these kinds of models is basically figuring out, hey, what should this sigma 1, sigma 2, sigma 3 be? How should I add this kind of noise? What should I perturb? And so forth. OK, cool. So now we're ready to actually start the process of the other kind of generative model that uses diffusion. So far, we've basically used a bunch of different tricks when it came to adding noise. And we said these tricks are nice because they let us sort of explore more of the data space, and they also let us actually estimate this score function that we had before. So this wasn't a totally connected way of using the noise, but they did help us in various ways. So let's just try to do something more direct with this rather than this version of things. And this will basically lead us to a simplified version of the fusion models, which are now very, very popular. So now we're going to do a different version of things. It's not going to have the same form as what we've seen, although in a sense it's actually equivalent. So the version that we're going to do is now going to just directly incorporate noise into a simple graphical model, so a simple stochastic process, which is what you're seeing here. We're no longer going to talk about this score function. We're not going to bring in this this iterative process for sampling. We're going to do something direct instead. And this direct thing is going to follow this procedure. It's going to look like the following. If we start with noise, we are going to follow one step to denoise it, follow a second step to denoise it, keep going until we get back to the original image. And the reverse version just says add a little bit of noise, add a little bit of noise, add a little bit of noise. So this is kind of what we started with when I showed you the first figure. And this turns out to be actually quite similar to the score-based version, but this kind of sidesteps some of those details. Everybody okay with the idea for the time being? Go for it.
Does theta vary with t or no?
Theta are going to be the parameters of the model that does this. Oh, no, right? We're not going to have a separate thing for each of these steps. That will be too complex. But yes, think of this p theta of xt minus 1 condition on xt as some neural network, right, that's parameterized by theta that we're going to run repeatedly. Cool. OK, let's see the details of this. So think of this as a graphical model, which granted we haven't talked about too much. But basically in a graphical model, we have a bunch of random variables. And each random variable pertains to things it's connected to. So in other words, the edges that connect it in the graph. And that's exactly what's happening here. So each of these guys is basically totally independent of everything but its neighbors. It has only a relationship with its neighbors. And this whole thing lasts for capital T steps. It starts with noise. You have this forward denoising process. This is what you do when you're sampling. You start with noise on the left, and you take capital T steps of denoising to go ahead and get an estimate from your original distribution. And then you have the reverse version of things, which we'll use in training. This reverse version of things says, OK, start with some sample from your true distribution, and then go ahead and add noise to it. And each step adds a bit more noise, and we'll see exactly how much noise we add. But in the end, we'll get back to this place where we have nothing but noise. So we have two processes here. They basically correspond to the two kind of functions we saw before. Something that maps us into the latent space. Here is just a noise space. And something that takes us from the latent space back to the original data space. That's exactly what we're doing here. So the p theta over there is going to take us back from noise to something in the true distribution. And the q over here will do the opposite. It'll take us to the noise space. OK, everybody OK with that? So those are the only two objects that we care about here. Now notice that only one of them is going to have any parameters. Why is that? Yeah?
Because adding noise is a free action.
Yeah, I don't actually need to parameterize the process of adding noise. There's nothing in there, right? I'm going to fix some noise schedules, which correspond to what we talked about right before. And I'm going to define this function q, and it'll be fixed. There's nothing to learn. But of course, I will need to learn p theta, right? So I'll need to learn those parameters. Otherwise, I won't be able to recover anything. Cool. OK, so let's see what this ends up looking like. OK, so this noising process is going to be extremely simplistic, basically. I'm just straightforwardly defining the thing that you're seeing on the bottom, which takes in the previous step and adds noise into it to get the next step. It's going to be, as you might have guessed, just a Gaussian. So here, for me to sample xt conditioned on the previous noising step, xt minus 1, all I'll go ahead and do is take the original xt minus 1 that I'm getting as input. I will normalize it by a little bit, and I'll add some noise to it. I'll try to control the overall variance, right? So that's why I'm doing this multiply by square root of 1 minus beta t, right? You can go ahead and compute your expected variance to keep it constant. And I'll just repeat this process. The only thing I have to do is to figure out, what should things like that beta be over there. And this is kind of up to me. I can decide how much to take from my original image versus how much to add noise. That is exactly what you're seeing there. For example, suppose that you set beta t to be equal to 0. How much noise do you add? What's the variance in that case? All right, if beta t is 0, what is beta t times the identity matrix? It's a 0 matrix, right? So my variance is 0. So if I set beta t to be equal to 0, I actually don't do anything. I add no noise whatsoever. Each step does nothing. So if my beta t is small, I'm taking these tiny steps where I'm adding a very small amount of noise, not much else. Now let's consider the opposite, right? Let's suppose that we make beta t to be equal to 1. What do I get in that case? All right, what's square root of 1 minus beta t? Right. So what's my mean in that case? 0. So then I'm ignoring the previous image, and I'm just sampling noise directly. So this is the range that I can get for these betas. This is the noise schedule. If I make this guy 0, then I'm not doing anything. If I make it 1, then I'm forgetting my image altogether and just in one step doing noise. So we'll want to be somewhere between these two extremes. If I never add any noise, then this process will take forever. If I add so much noise in one step, it will be impossible to recover. When I go train my p theta over there, the process that tries to undo the noising, it's going to be extremely difficult for us to be able to do that because we've forgotten everything by going from xt minus 1 to just pure noise in xt. OK, so everybody comfortable with what we are sampling from in this conditional distribution here? It's literally just take the original image that we got, or the previous step. Let's add noise to it, and we'll control the amount of noise that we add. And that's it. OK, now we can see this is just for one step. Naturally, we're going to do this for the entire chain. But everything is independent, so it just all multiplies together. It's just chain rule. That's what I meant by this is a probabilistic graphical model. Those arrows tell you that you're independent of everything except the thing you came from. And therefore, for my final step on all my vectors, is just a multiplication of all these guys. OK, everybody OK with this part? Yeah.
So I guess when we're trying to compute theta and repeat theta, like, is it just taking the inverse of qxt over xt?
Basically, yeah. Yeah, nothing very interesting is going to happen when we do that.
And we're just going to, those are basically our inputs to the model where we try to compute theta.
Mm-hmm.
That's nice.
OK, so for sampling, right, this is the process of adding noise. For sampling, I'll just go ahead and do the opposite, right? So the reverse, exactly as described it, right? Q of xt minus 1 condition on xt over here. Now, OK, it'd be nice for us to write some expressions for what this actually looks like. And conveniently, there are some nice parametrizations that we can actually go use. So really, we don't have to worry too much about the details. There's a nice way of expressing both directions. And this permits us basically to just go ahead and run a simple training process. And then we can go ahead and sample just by doing run those p thetas over all of your steps. Now, the only real details is how many steps should you take to get high quality outputs, right? What is the relationship between capital T and how good of a job you did modeling that original data distribution? And correspondingly, what beta t's should you pick as well? So that's pretty much what all the game is going to be about, figuring out those details. Otherwise, the mechanics are pretty trivial. And this is all surprisingly scalable as well. OK, now I want to talk about one more thing. Again, one difference that we saw here is there's no clear notion of a latent space that is distinct from the original data space. We just said, hey, let's noise everything in our original data space and not much else. Now, folks have thought about this as well. And you can indeed incorporate a latent space into this as well, right? And we can do this basically by adding another piece from a generative model, like an autoencoder, right? So then we'll have something that combines all the things that we've talked about so far, right? We can basically say, hey, first, map yourself to the latent space using any of the tools that we've talked about. And then let's actually do a diffusion process in that latent space. After all, we're still some vector in the latent space. We can still go from there to noise. And we can still go back from there as well. And then we can go ahead and reverse map ourselves from the latent space to the original space. Now, why would we want to do this? Well, it turns out that indeed in the latent space you have more control over a bunch of pieces. And you can hook up things like text, for example, as well. I can map text into my latent space and get good control over what's going on there and run my diffusion model there. So latent diffusion, which is a very popular paper, did exactly this idea. And as I mentioned, this is pretty useful for text to image, right? The basic idea is incredibly simple, right? You're just going to go ahead and grab your encoder. This is going to permit you to go to this latent space where you're doing diffusion anyway, but it lets you do whatever modality you want to handle there. You just have to encode your text into that latent space. So this is exactly the stuff that we talked about when we were talking about multimodal models. Okay, and I think that's pretty much all I wanted to say for diffusion models. They're basically the simplest and most scalable form that we've seen so far from all of our generative models. They just have this annoying caveat that you might have to take a lot of steps. And figuring out how many steps you should use for your diffusion model is sort of the main challenge. But otherwise, it's compatible with everything we've talked about. You can make them multimodal in the text-to-image sense or anything else too. Any questions before I move on? Cool. All right, so finally, we're ready to start today's lecture. So totally different topic, although it connects. We're now going to talk about how do we know what kind of choices we should make for when we go ahead and design and train our big models. And of course, the trends are exactly the ones that we've seen so far in our class, right? Getting generally bigger has been the usual trend. What's interesting is that this paper is actually looking at things up till 2022. And it's showing you kind of different model classes. This is a picture with all the models out there. You have this original sort of linear looking relationship if you go back to like the beginning of deep learning, like in 2010. So this chart starts in 2008. And then it clearly changes slope or something, right? So if you're looking at 2020 and onwards, you have a more steep kind of curve. If you do piecewise, right, you can actually separate it into these two parts over here. So this is actually pretty interesting, right? Like you have two sort of general changes. Now, of course, at the same time, you can't go too big either, and that's sort of the other trend of the last year to 2 years. It's getting to be both increasingly intractable to make models much bigger than 1 trillion parameters, and also there's some diminishing returns in pre-training above that trillion parameter range anyway. So models have gotten much bigger, but we're starting to level off anyway. Nevertheless, as long as you're doing 100 billion parameters plus, again, you have to be very careful because you do not have too many training runs you can do. Okay, so similar story for compute. We just saw model size and parameters. We also have more hardware to do compute with as well, right? So you probably have seen all these stories about how quickly people ramp up and build clusters that have tens, hundreds of thousands of GPUs that you can use. Again, this is from a couple of years ago, but very similar story in general. It doesn't take too long, and you can get up to 100,000 of these GPUs, which permits you to train fairly large models. And same thing with data, right? So this is the other trend that we've seen in this class, right? If you look from kind of earlier things, you get fairly small numbers of points, which is that instance column. 2,000, 9,000, 100,000. ImageNet is this huge jump to 15 million. And these are still labeled data sets, right? If you compare it to unlabeled data, like our giant corpora from the internet, we can obviously go even way bigger than that, right? So we're going to soon have pretty much all the data we'll ever get. You guys should check out this paper because it's pretty fun. Will we ever run out of data? It's kind of an interesting question that becomes relevant for some of these models. OK, so the story so far is we have really big models, lots of data, lots of compute. The question becomes, how should we allocate our training, especially when it comes to something expensive like pre-training? Should I, for example, decide that I'm going to use the biggest possible model size, and that takes a lot of compute to train it all, so I'm going to do fewer epochs of my data? Or should I pick a model that's slightly smaller that permits me to use compute more efficiently, and I'll do more epochs of that data? Right? That's one example of a choice that we'll have to make. Everybody see what I mean by that? So you could imagine, for example, a model of 100 billion parameters, and I can afford to do one run, one epoch for my data. Or maybe a model that's 30 billion parameters, but I can do 2 epochs. Which one's better? And the answer is we don't know, right? A priori, That's not a very simple question to answer, and we do not yet have a very rich theory that can simply spit out that answer and tell you what to do. So what we'll do here is try to answer that question at smaller scales and try to extrapolate from that to the actual scales that we care about. And that will hopefully give us an answer to this question. So this is going to be the subject of all these scaling laws that I'll talk about. Does that make sense for everyone? All right, so let's take a look at it. Okay, so we want to understand how performance is going to scale with these three quantities that we've talked about, which is to say compute, literally how much training you do, how many flops you incur, how big our model is in terms of number of parameters, and how much data we're going to look at. So we want to understand how performance scales with these things, but not just sort of independently scales with these things, but also kind of how they interact, right? Should I do more of A and less of B, or the other way around to maximize my performance subject to some constraint? And the way we'll answer this question is by drawing plots that look like this. This is from a very popular paper that we'll spend some time looking at. What this is showing you, for example, if we look at this middle curve, is they basically ran all of those points over here. They said, okay, fix everything else. Let's look at varying the data set size. And let's see what happens to the performance of our model in the sense of test loss as we increase that data set size. And not surprisingly, the test loss goes down. That's good, right? If we see more data, we should hopefully get better. But the question is, well, what is the function that describes that relationship? And the one they picked is this thing called the power law. You're seeing it over there. And it's actually a reasonable fit, especially as we get into larger amounts of data. And here we're tracking literally numbers of tokens that we've seen, starting with something like 10 to the 7, 10 million, going to 100 million, going to 1 billion, and so forth. So this is very useful, right? I can take this curve that I've learned, and I can plug in a much bigger number. For a full-scale model run, I might train on maybe 10 trillion tokens. Now, this guy over here, the points that we got were for much smaller scales. But if I can extrapolate outwards, I can guess how good my performance will be with my 10 trillion tokens. So that's going to be what we're going to do here. Literally fit curves and hope they extrapolate correctly. Everybody agree with that? Now, this might seem, not extremely scientific, and in some sense it's not, right? But it actually does give us quite a lot of signal. And these scaling laws turn out to be fairly reasonable. They are not really way off. And I think that's something that's actually very interesting. And we'll see a bunch of examples of these. And here you're seeing independent scaling laws that are tackling everything. How much compute, how big is the data set, how large is the model, but everything else is fixed in place. OK, everybody OK with that? We're going to get into the details, so bear with me. So the scaling law idea, by the way, is actually not super unique, really, to anything in machine learning or AI. It came from a lot of different places. But basically, people do similar things all the time. I'm going to pick an example from a different area that's called error-correcting codes. So error-correcting codes are basically saying, I am going to go ahead and essentially add some redundancy to some message that I'm communicating over a noisy channel. Like, for example, if I do a satellite communication, I have to transmit some information from where I am to something that's thousands of miles away. And the process of sending it over the air or for whatever other channel, it incurs some noise. Some aspects of my message will get corrupted. Now, I can add some redundancy. I can say, hey, double my message, repeat everything I'm saying twice. And if something's corrupted, hopefully I can recover from somewhere else. OK, so the question is, how do I add enough redundancy, right, that I'm going to be able to communicate correctly while not having tons of overhead? I don't want to have to repeat my message 10,000 times to communicate the same one. So what this plot is showing you is basically telling you, well, depending on how much redundancy you're willing to incur, this is measured in what's called the signal-to-noise ratio, then I'm going to be able to see some probability of communicating without error. And what you're seeing here is for this special class of adding redundancy that are called these codes, first, initially, you say, oh, OK, well, things are going really well. Right? I'm able to reduce my error from 10 to the minus 1 to 10 to the minus 8 with very, very little overhead, basically. I can go very fast. I can get huge gains in terms of how much more efficient, how much more correctly I communicate. Now, unfortunately, afterwards, the curve starts sloping in a very different way. I have to give much more for me to be able to actually get any benefit. So this is the example of a scaling law kind of relationship. In some situations, I get a lot for very little, but then in other situations, I have to give up a ton to get not too much. So this was something that was known in 1995. There's this cute story. The people who created this original scheme, they show the plot in their paper, but they cut themselves off right over here. So exactly as things were going down in this very favorable way, they showed that part of the picture, but although they knew things would flatten out and be much less favorable, they cut that out. And someone else had to go, rerun the experiments and see these details. So anyway, no one do that because it's also kind of dishonest, but it is a pretty funny story. Okay, so this is an example of a scaling law from something else. Now let's return to the more machine learning AI setting. So this paper is one of the most popular ones that basically introduce scaling laws for the thing that we care about, which is for neural networks. And specifically, we're going to run this for transformers and sometimes for other kinds of neural network architectures. Okay, so very popular paper. Now let's kind of establish some of the pieces that we're going to use to measure these scaling laws. For compute, the unit that we'll talk about is floating point operations, so flops. So we're not going to talk about how many iteration steps, things like that, because those are also kind of a function of other things like model size. Flops is going to be an independent measurement unit, right? It's just literally whatever our GPU can handle. Next, we have model size in parameters, as usual. This is just a standard thing we talk about when we say billions of parameters. And we're mostly talking about pre-training. So let's just talk about tokens here. Literally, the number of total tokens in your data set is going to be how you measure data. And for ranges, for this paper at least, we'll start with some models that are incredibly tiny, less than 1,000 parameters, and we'll move all the way up to 1.5 billion parameters. We are only going to count non-embedding parameters here. So of course, there's another question of, well, how big should my embeddings be as well? We're going to ignore that here. Okay, for data, we'll start from millions, so 20 millions, all the way up to tens of billions of tokens. Again, not too big. And then we'll talk about compute in just a second, but these are the ranges that we're looking at. Now, again, you might say these are very small compared to the sizes of models we'll do. That's true, but that's exactly why we want to do this. We'll be able to run many points and fit our curves, fit our scaling laws, because these are not extremely big numbers. Okay, everybody agree with that? All right, so let's go ahead and look at flops. It's floating point operations per second, which is exactly what we talked about. Right? Pretty much everything we're doing is going to be one of these kinds of operations. It's all adding and multiplying real numbers. And our standard approach is 32-bit. Of course, there's quantized versions that people often work with, so keep that in mind as well. Okay, so what kind of flops can we do on maybe a consumer level GPU? And the answer is kind of the following, right? You can do 80 teraflops, right? For example, on a pretty standard RTX 4090. This is a consumer GPU that you can go out and buy. So you can handle quite a large number of these guys. And the more GPUs you have, of course, the more you multiply your flops per second. Cool. All right, so we have all the units. So now we kind of know what to measure and what to compare. The next question is, if we are going to fit curves, well, what should they be, right? We have to make some choices for how we're going to fit them. And we're going to pick this concept called a power law. Power laws show up all the place in various kinds of modeling, right? It looks like this always. I have some x I plug in, and my relationship for the output is always going to be take my x, lift it to some power, and then go ahead and multiply it by something. Everybody okay with that? So you see this all the time. There are many distributions based on this concept. We're going to give these guys names. The coefficient will be the a over here. I'll call this minus k the exponent. Everybody okay with this? Okay, so this is going to be some nice simple exponential function, right? And then, therefore, we're going to end up being able to fit things that look something like this, right? Let's suppose that I'm tracking the number of parameters n, and I want the output to represent my loss for a model with that many n parameters, right? Then I'm going to get an expression that looks like the following. I'll do nc divided by n, all raised to the exponent alpha n. It looks slightly different in the form up there, but it's actually not too different. I've just put this nc inside the parenthesis instead of moving it outside. Everybody see what I mean? This thing is like nc to the power alpha n over there is just your alpha. or your A on top, and then this alpha n is your minus k. That's all that's going on here. Okay, now let's sanity check this. Does this behave the way we'd expect? If n gets larger, this expression, what happens to it? Fix your NC and alpha n. These are just some values, right? And of course, your alpha n will be negative over there, but yeah. Okay, yeah. So if I make n bigger, then L of n will get smaller. That checks, right? I expect my loss to go down if my model size is bigger. Now, you might say eventually this will break down potentially, and that's true. This is in whatever range we're getting a larger model will make sense. Okay, so let's see what these things look like. My alpha n here ends up being, from fitting these points, 0.076. Usually has to be something small. And my NC will be something very big because it's comparable to n, which is large. So it's something like 9 times 10 to the 13. Again, where did these values come from? Well, we basically picked a bunch of different models with different sizes. We trained them under the same conditions. We got their loss value, that L of n, for these guys. And then we go ahead and fit that function over there, that power law, so that it fits as closely as possible all these points that we got. So literally, we're going to train two parameters, our alpha and our k, right, in such a way that we fit as closely as possible. Right, and it's exactly the things that we've seen before, coefficient and exponent over here. Okay, so let's also kind of get back to why we think this would make any sense. And as I mentioned, what do regions also have any sort of logic here? So this is a paper that's actually pretty old. It predates all of this idea of scaling laws for neural networks for transformers. It's basically saying, look, my expectation when I scale, let's say, the data is something like the following. First, I have only a tiny bit of data. I can't really learn from it. There's not that much I can do. So the best I can really do is make some guesses. And therefore, initially, as I increase the number of data, well, I don't get too much, right? I'm basically flat, right, when it comes to my performance. So this makes sense. When I see just a tiny number of points, there's not that much I can do yet. Then I start being able to actually go ahead and fit my model. And the more points I get, the better my model gets, right? But this is that power law region that we've been looking at in the previous plots. If I'm in this regime, as I get more data, I get better performance. Now, eventually, I'm kind of constrained by my model's capacity. I cannot do much better. Even with access to all the points I can possibly get, I end up having some irreducible error, right? This is the gap between my hypothesis class and the true function that I'm trying to represent. There's nothing I can do about this part. Even seeing more data doesn't help me do anything. So over here, I can't do too much until I get more data. Over here, getting more data doesn't do anything for me. But in this middle region, that's where I get this power law relationship. And all the things we're doing are going to be tracking that middle area. All right, everybody okay with this intuition? And you see this, of course, when you train your own models, right? Initially, if you have no data, then you have a very bad model, no matter what. Eventually, you've shown it all the data. You get diminishing returns, and nothing good happens. But if you're in that middle region, there's a lot you get from adding more data. And it's going to be the exact same story, not just for data, but for all these other quantities that we're tracking as well. Cool. Everybody okay with this so far? So one question for you guys. Can I use this power law notion to fit the small data regime or the irreducible error regime? Who thinks it's yes? Who thinks it's no? All right, a bunch of people. Why not? Yeah, so if we look down here, this is log scale, which is what we'd expect. This power law is exponential. When you take the log, it's something linear, right? And therefore, you're going to get something like this, but that is not the shape that we expect to see either here or here. It would have to be some other relationship. It couldn't be a power law. It would have to be something else. So we're really only going to care about this middle power law region. OK, let's go ahead and get to it. Let's go ahead and vary the model size and kind of look at what the experiment looked like that they did. This is all coming from that same paper, the Kaplan 20 paper. OK, let's go ahead and first fix these other quantities. Right? We're deriving a relationship where there is one independent variable. And that one independent variable is just going to be the model size, this capital N. So we have to fix everything else, right? And first, let's fix our data set. And naturally, we need it to be large. Again, otherwise we won't be in the same regime. If I have a very small data set, then changing the size of the model doesn't really do anything. We can't really learn, right? If I have a data set that's kind of varying of the size of the model, I have two relationships happening, and that's more complicated, right? We'll model that later. So right now, let's give ourselves a big data set, and let's say it's fixed. And all of the different size models that we run will be using that exact same data set. OK, so now let's vary our model size. As I mentioned, something tiny, below 1,000 parameters, all the way up to 1.5 billion parameters. We'll sample some model sizes in that range. And we'll measure our test loss, right? We'll have some test set. And we'll go ahead and measure our loss function on that test set for each of these guys after we've trained them. And then we'll go ahead and just draw all the points. All of those points you're seeing over there, those circles, those are just different losses that we end up getting for different model sizes, starting with that left top corner, that's 1,000 parameters or less, all the way up to this billions of parameters, 1.5b, which is the bottom right. And the curve that we get, again, from this space of power law kind of functions, is that guy that we saw over there. So again, we're dividing by something like 10 to the 14, and then we have this exponent of minus 0.076. So this is the curve that best fits that graph over there. And indeed, as expected, because we are writing this on an exponential scale, so this is log scale over here, we get something that looks pretty linear. All right, so what would we use this for? Well, let's suppose I really did already have a huge data set, and I was trying to figure out how much do I get from doubling the size of my model, right? I've already trained the model at, let's say, 10 billion parameters, and I want to understand how much better will be a 20 billion parameter model than the one I currently have. Well, the convenient thing is this relationship tells me that information, right? All I have to do is to say plug in something twice as big into n and see what change I get. Everybody agree? So this is very valuable. In fact, I can say, hey, I can handle a model that's 300 billion parameters, let's say. That's approximately what GPT-4 was, right? I can use this relationship and say, yeah, I expect the loss to be this much. Now, of course, this doesn't help me directly because maybe I don't care just about the overall loss. Maybe I care about how accurate I'll be on various tasks. Well, I can then have some other proxies that say if I can achieve this loss, I can get to that level of accuracy. So I can essentially reverse engineer my expectations for my model as a function of its size using this kind of relationship that I've gotten. Any questions about this? And again, you could actually do this at home for small sizes. Nothing is stopping us. The only problem is we probably can't train anything beyond the first 4 or so points over there, or maybe a few more of them. But as you can see, they're not too bad. The relationship won't change too much. So we really can do this quite often and get some reasonable results from it. Cool. And what does the curve look like? Exactly the one that we talked about over here. All right, so this is one type of unit. This is just model size. Let's play the exact same game, but this time let's do it for the data set, right? What was our unit of measurement for data set size? Yeah, number of tokens. Same exact principle, right? I'm going to fix my model size this case, right? Again, I have one independent variable, so everything else has to be held constant. So in this other case, I no longer say fix data set, vary model size. I'm now fixing my model size, make it big, and now I'll change my data set. Cool. So let's go ahead and do it. Let's vary our data from 20 million tokens to about 20 billion tokens, so a range of about 1,000. Same deal, measure my test loss. Same basic idea. I'll get a bunch of these points, and then I'll go ahead and fit one of these curves. And I have a very similar looking relationship. This time, D over here is data set size and number of tokens. So my independent variable is this D over here. I have my coefficient over here, my DC, and my exponent alpha D. The alpha D is 0.095, and my D is something like 5 times 10 to the 13 number of tokens. So same deal here. I can now ask myself the question of, OK, well, I have this model. It's the size I want it to be. What does doubling my data set buy me? If I go and scrape twice as many tokens off the internet, what do I get from doing that? And I can establish that by just plugging into this formula, right? Instead of having some D over here, I'll have 2D. and I'll see how much that buys me in terms of the loss. And that's literally given to you by this relationship. And this exponent kind of tells you that information, really. Everybody okay with that? Okay, so this is already pretty valuable, right? We can predict lots of things about what's kind of good for us to do. I know how much I'm getting from increasing the size of my model. I know how much I'm getting from increasing the size of my data set, et cetera, right? Everybody agree? Cool. So this also tells me quite a bit. Now, the nice thing is I don't have to do a bunch of these things independently. I can start creating scaling laws that incorporate multiple terms. It doesn't just have to be model size by itself, right? And data set size by itself. I can do everything as well, right? Okay, so let's take a quick look over here. Here is a function that incorporates more or less everything that we have so far. I'm plugging in two pieces, n, which is the size of my model, and d, which is my data set size. And not surprisingly, I'm going to have kind of a coupled power law over here. So I have my original nc over n. This is lifted to this exponent alpha n over alpha d, plus my dc over d, and the whole thing to alpha d. So I'm permitting myself to now have interactions. And therefore, I'll have this sort of two-dimensional plot, right? Because I'm varying two things currently. All of these colors for the different sweeps, these guys pertain to the number of parameters. And I'm still measuring the number of tokens here on the x-axis. But again, I now have two quantities I'm varying here, right? So this is kind of a two-dimensional plot. One is given by which of these colors you're seeing, and the other is given by how many tokens you're looking at. And I'm still measuring the loss. Okay, now why would I care about doing this? Well, the basic answer is I have to make a choice, right? I have some fixed budget, and this fixed budget is going to go into things like getting data, and it's going to go into things like how big my model can be. And I have to make some decision about which of these things I want to prioritize. So I do want to see over here, for example, how they interact, right? And this tells me a lot, because it's basically telling me, hey, for different model sizes, how quickly do I actually start not really caring about increasing how many tokens I get, right? So we can see over here that for a small model, I burn out very quickly. For example, for models that are much larger, then it makes sense to keep going down, at least for much longer. So I'm getting a ton of information here, and I kind of start figuring out where to invest my budget, basically, right? Okay, everybody okay with this kind of plot? Okay, now so far we haven't even incorporated the third piece, which are dealing with compute, right? Now, there's one thing that's very annoying about compute that makes life slightly more complex. For example, for data set size, that is totally independent of anything else. It's just how many tokens we have, right? There's no interaction directly between that and how big my model is. And for my model size, it's also totally independent of data. So these two things can be completely independent variables. I don't have to worry about them mixing in any way. They don't affect each other directly. Everybody agree with this statement? Now, for compute, unfortunately, it's not really independent, right, of the model or data set size. If I make my model bigger, then, for example, each of my forward passes costs me more compute. So it's not something that I can completely independently vary, right? The bigger my model is, the more it affects this kind of thing. And we're going to have a very simple equation for compute. It's a very rough heuristic. It's not, perfect by any stretch here. We're going to have the compute quantity is going to be equal to some constant that reflects forward and backwards passes. That's going to be 6 here. The details aren't super important. We're going to have it be related to the number of parameters, because again, the more parameters I have, the more operations I'm stuck doing. It's going to multiply that times the batch size, because when I'm doing training, I'm not just doing one point at a time. I have some number of points in my batch. And finally, the number of steps that I want to take, right? Because again, I might choose to take fewer or more steps overall. So here's our equation. Compute is going to be given by how big is our model times how many points we're putting into our batch, and that's kind of up to us. I can do smaller or larger batches. And finally, how many steps I want to do. So this is going to be our rough formula, but again, it's actually dependent on the number of parameters, which is to say the model size. And notice that indirectly, this also kind of reflects the data set size as well, right? If I want to do a full epoch, then I have to compute how many points I put in a batch size and how many steps I take. Everybody agree with this? And this number 6 is really coming from the fact that the forward pass is about half as expensive as the backward pass. You can ignore it. There's far more refined calculations than this. OK, cool. So how do we set the batch size? All right, what's the most simple answer typically for you guys?
Fixed size. 1,000.
OK, if you go and train a model, like let's say you pick a ResNet and you decide to train an ImageNet, can you typically do a batch size of 1,000?
Probably not.
All right, so how would you pick your batch size given that constraint?
All right. VRAM constraints then.
Yes, yes. Yeah, so the typical way we pick our batch size is make it the biggest that fits your GPU, right? That is the typical simplest thing to do. Now, of course, if we have a cluster of 20,000 GPUs, it's a different story. We can actually think about how to pick a good batch size because we have the option. And it'll turn out there is really an optimal batch size that makes sense. One that sort of says, hey, not too big, because it turns out that approximating gradient descent, which is what you get from a very large batch size, is not great. And not too small, because then you need too many steps, of course. So we're going to end up having a bunch of sort of rules for how to set this B. It will not be some completely independent quantity either. OK, now, finally, the number of steps here, as I mentioned, it really is a function of, well, how long do I want to do this whole thing for? If I want to do it for some fixed number of epochs, that will determine the number of steps. If I want to do it until we converge, independent of a full epoch, again, I'll have some stopping rule that determines this number of steps as well. So this thing itself is unfortunately something else that we have to bring in some experience, some rule for it. Cool. OK, so we'll typically use this sort of good batch size that I mentioned that we can do, which is called this critical batch size. And then we're going to go ahead and kind of have all of these different parameters expressed as a function of the things that we care about, right? OK, so we're going to end up being able to fit all these guys. And roughly what we end up getting is the following set of relationships, right? As our compute increases, it turns out that it makes more sense to spend it on larger models, right, without necessarily doing longer training time or data set size. So this is a statement I'm quoting from the paper, but it's actually a direct reflection of those coefficients. All those coefficients you're seeing over there, they're basically telling you, well, what do you get as you put more stuff in? As I put in more compute, or as I make my model larger, or as I make my data set larger, how much do I get? And the best exponent tells you what you should invest in. And that's what the conclusion is reflecting over here. As we get more and more compute, what we should really do is don't do more data and don't do more epochs. Instead, get a bigger model. And this was the main conclusion from the first of these scaling law papers. And this was something very influential, weirdly enough, right? You might think of this paper as some kind of curiosity, but this inspired everyone to think that you really, really, really should be looking at scaling up model sizes. That means you should not be using, a smaller model and doing more training on it. You should not be doing a smaller model and invest in a way bigger data set. As you increase your compute, just make sure you get a bigger model and just try to keep the other things in pace with it, but nothing else. So this is something very, very interesting as a result. And this is why people thought we would be going to 10 trillion, 100 trillion parameter kind of models. The scaling law relationship really suggests that's what you should do. OK, so one more thing I wanted to show before we end up taking a quick break as well, although we're almost at the end. For architectures, so far, really, all of the things we've talked about apply to transformers, but you could get the same relationships for any other model architecture as well. And this paper actually did a computation of transformers versus LSTMs. LSTMs being the previous sort of best type of language model that we can use. And it's quite interesting. This is just showing you model size, although we can run any of the other measurements as well. What you're seeing over there for LSTMs is essentially they do have a similar scaling relationship, which is to say if you get your model to be bigger, your loss goes down. But notice that it's not on the Pareto frontier, right? It's entirely above the curve that you get from running transformers, the blue curve. So what this really is telling you is, hey, there's a real advantage to transformers, right? Like you don't have any reason to use an LSTM or some pre-transformers kind of architecture because you're actually never going to be optimal, no matter how big of a model size you're looking at. So this is a pretty interesting conclusion. Now, with the return of all of these sort of like new versions of RNNs, SSMs, all these other models that we've talked about, this plot is not strictly accurate anymore. We'll have other things in our frontier. So that's something fun to think about. But this plot really convinced people when it came out 5 years ago that transformers are the way to go, and there's no good reason to think much about other architectures. OK, everybody good with what we've talked about so far? Could you draw your own scaling law for some super miniature models, for example? Awesome. OK, so nothing super interesting about this. All right, let me mention one more thing. Basically, the whole point of these guys is just to go ahead and kind of predict, right? You train smaller models, you get your scaling law, and you make some design decision based on the scaling law, and then you pray to God that it was good, right? Like that's what you have to do here. You really actually do not know in advance whether whatever point you're extrapolating to is still part of the original relationship, right? As we saw in the other case where we had these different regions, and our power law region was just kind of part of it, it's entirely possible that if you extrapolate somewhere, you end up being off of the power law area, and you don't get the results you're looking for. So this is kind of the scary thing about these things. If someone does like actually go do a 100 trillion parameter model, it may not perform as well as we had hoped. In fact, there is speculation that people have tried things like this, like companies like OpenAI, and the results were disappointing. In other words, the scaling law they derived wasn't holding anymore. So something interesting to think about, especially if you guys go become engineers or researchers in these companies. OK, we're running out of time, so let me take one question from anybody, and we'll kind of power through. Anybody have questions? Cool. All right, let's keep going. What we're now going to talk about is another paper that's also very popular, and that challenges some of the results from this first scaling laws paper. And this second paper is really the one that almost everybody kind of uses to make decisions today. And it has this somewhat funny name. It's called Chinchilla, because that was the name of a model trained using the techniques from this paper. OK, so this is exactly what we talked about, right? What is the implication of these scaling laws? How universal are they really? How much can I really depend on them when I go scale up my models, right? And the biggest issue here is that we've made a bunch of choices, right, in this process. We had to, right? We had to fix everything, make everything constant, except the things that we were varying. The model size, the number of parameters, the data size, et cetera. So for example, they used things like early stopping. Of course, you could ask the question of, well, if you use some other termination condition, would you get the same curves or the same results? And if the answer is no, then you really now have no way of knowing what's going on in this other regime. They used, for example, for tuning the learning rate, a very particular schedule. You could do something different, and that conceivably would result in other types of scaling laws, right? So this is something that's actually quite tricky. And there's another nice paper, which is also now a few years old, that has slightly different results. This one's coming from DeepMind, and it's this Chinchilla paper that I mentioned. So what they decided to do is to get a bit more evidence by using multiple methodologies for deriving these scaling laws. And they essentially used 3 different approaches. And what they sought to look for is, do these 3 line up? Do you get kind of similar results when I use all 3 of these guys? And if so, then we can have a bit more confidence that there's something more universal happening. And if not, then all bets are off, right? We better train models with exactly the same conditions as the scaling law ones. OK, so here's going to be their first type. This was going to be called, let's do a minimum over curves. And I'm going to show you what this thing looks like. So for each number of parameters, they're varying. Very similar to the last paper, right? They're changing 70 million to 10 billion for being the parameter size. They're going to vary the number of training steps. They'll do a bunch of these training sequences, take the best one overall. And they'll train exactly the same kind of power law that we had before, but just using this principle, right? And the interesting thing here is they find exponents that are slightly different. So we have in the left column over here, this is for model size, the n. And in the right column over here, this is for looking at the data set size, the d. And what's interesting about their findings compared to the paper we talked about, the Kaplan one, is that one said, hey, over here, the model size has this big exponent. This buys you a lot when you double the model size. The data set size has this small exponent. This buys you much less when you double the data set size. So if you're choosing what to double, you should double this guy, the model size. And that was exactly that conclusion that we talked about, right? That all things being equal, I want a bigger model. What's interesting about this paper's results is they got 0.5 and 0.5. That's actually much more magical, right? That says there is no great advantage to making your model bigger versus making your data set bigger. Both can work. You're roughly getting the same kind of scaling relationship with these. Everybody agree? Now notice that they're not writing down the values of the coefficient, but that's because that's not the important thing, right? We're really asking, when I grow the number of parameters or the data set size, what do I see? The coefficient itself doesn't tell you that. So this is the exponent. That's the thing that we really care about. OK, a second approach has this funny name. It's called isoflop profiles, right? We fix the number of operations we're allowed to do, and again, do things like vary the model sizes. And you get these kinds of relationships over here. And why is it a U shape like that? Anybody have a guess? Again, all of those different guys are saying, I'm going to vary the number of parameters for a fixed budget of compute, for a fixed number of operations I can do.
Your model's getting so big that you're running out of compute to effectively train it.
Right, exactly. So initially, I have plenty of compute, but my model's tiny, so I don't get too big of a benefit from it. Then my model gets bigger. I'm investing my operations perfectly into it, so I'm getting better. Eventually, my model's getting so big that I can barely train it under this amount of compute, so I don't get much. So I get these U-shaped guys over here, right? And these show me the whole relationship with respect to compute. And one thing I can kind of do is I can take the bottom of all of these guys and connect it. And that's my scaling law. It's just saying, hey, this is the optimal thing I can do under various compute budgets. OK, and then we can get the same kinds of relationships as before. Interestingly, this approach as well is giving me something very similar, 0.49 and 0.51 for my exponents. So we're getting some consistency between the different approaches, which means maybe they're not very methodology dependent, but these are consistent among themselves. They're still different from the Kaplan paper. OK, so another interesting finding. And finally, we can just go fit some curves in the more standard classic way over there. You actually get something also pretty similar, 0.46, 0.54. OK, so the story so far is it seems like, one, there's some consistent, maybe more universal results among these different methodological approaches for scaling laws. And nevertheless, they're pretty different from what we saw earlier. And the difference has big implications, right? Previously, we said make models bigger, 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 bigger. That's what matters. Now we're saying there's no great thing to do here. You can either invest into a bigger model or data. You should track each other. There's no gain to have from investing more into models. So this is something very interesting, right? Basically, this is the quote from the paper. All three approaches tell you the same thing, that roughly speaking, you should move equally, right? There's no benefit to just model size versus data set size. Both of them should kind of fit together over here. So quite a different conclusion from the Kaplan paper, and one that has extremely big implications for what you should do in a big training run. Right? If you trained a 20 trillion parameter model based on the first paper's ideas, that might have been super suboptimal. Really, you should have invested into a smaller model with way more data. So this is something quite interesting. They took this idea and trained a model. This model is called Chinchilla, right? And this model basically behaved better compared to the Kaplan type scaling curve than you would have thought it's possible. OK, now we're not quite out of time. OK, so here's kind of different models that you're seeing. What we're plotting over here is the number of flops, which is what you're seeing. And you're seeing a bunch of different models over there, right? So the green one is the Chinchilla one. All three of those other ones, Gopher, GPT-3, Megatron, whatever, those are based on the earlier training principle, right? The one with the Kaplan-style scaling law. And what you're basically seeing here is that you can get away with something that performs better by following this sort of more kind of, y equals x type of curve, right? Like if you see the other curves, they're saying, hey, increase the parameters, be on a steeper curve. But over here, we're on something that's actually much closer, right? And this will turn out to work better. And it's going to save us, fortunately, a lot of compute, right? So smaller is better over here. 70 billion parameters with 1.5 trillion tokens ends up being somewhat the same performance compared to a much larger model, which is those three guys that you're seeing over there. Cool. So, in other words, things are interesting. Some scaling laws tell you one thing. Other scaling laws tell you a different thing. I'll cut to the chase because we're out of time. This is the correct scaling law in much more ranges that we actually care about. So we'll often talk about designing what's called a chinchilla optimal model. Right? This is the scaling law that's largely used for everything that we care about. And next time when we reconvene, I'll tell you why, at least why we think this is more correct than the other version. So let's stop there and let's keep going on Thursday. And we'll somehow have to find time to do everything that's left because next week is going to be presentations. Cool. Thank you, folks. See you on Thursday.